Well, after doing 5 tedious equilibrium math problems, which actually I thought were kind of interesting, it's time to do something qualitative. This is known as Le Chatelier's principle. For all of the problems we were doing, we weren't really messing with the equilibrium, adjusting it to our favor. We were just figuring out, well, if you're stuck with it, what's going to happen? And chemists don't really want to be stuck with a lousy equilibrium constant if they're trying to make something. And so I always think of this, since I have a background as a synthetic organic chemist, is how can we modify an equilibrium constant to increase it or to eliminate it? And if you take that kind of attitude, I think it helps to understand these principles. So the basic ideas are these are strategies for adjusting equilibrium. We can do it by changing pressure, concentration, or temperature, usually in predictable ways, right? Increasing the pressure, increasing the concentration, oftentimes increasing the temperature. Oftentimes that works out, but there's rules for each that you need to be aware of, otherwise you can get the wrong answer, because it's not always true. By the way, if you look these up in a textbook, they have some strange explanation, in my opinion, about relieving stress. I don't like that at all. I just say you can mess with it using these 3 things. Okay, let's imagine we have a chemical reaction. A plus 3B, it should say there, is turning into C, and the reaction is endothermic, meaning it requires energy in order to occur. Much like baking a cake, it will not occur to any significant amount on its own unless you heat it, and so that's an endothermic reaction. Let's see what we can do. Let's imagine that we add some reactant. O, A, or B. Boy, I wish that B was written there. What would be the result? I think that would push it to the right. You know, if you add react, doesn't it seem like it would help add more stuff? And it does. The explanation that I'm going to give is called stoking the fire. Imagine this is a wood fire, you know, where you're taking some cellulose and you're reacting with oxygen, making carbon dioxide and water. If we add more wood to the fire, clearly it's going to push it to the right. And this sort of analogy works fine for this these qualitative understandings. By the way, why did we say that? PCT, Pacific Crest Trail, pressure, concentration, and temperature. So here we're changing concentration. If we add product, that's changing concentration of product. Well, that would be ridiculous. Of course, if you add product after it's done, well, it's not the chemical reaction, but you get more stuff that way. That's called cheating. We're talking about throwing product into the reaction mixture. We can all agree that would shift the equilibrium to the left. I would call that quenching the fire. Adding water is not a good idea for a wood fire. Adding carbon dioxide, which is fire extinguisher, is not a good idea for a wood fire. So use this analogy. Heat it up. That's an interesting thing. I never thought of heating up a wood fire. Well, this is not, wood fires are usually exothermic. This happens to be an endothermic process. The general rule is heat it if it needs it. This thing needs heat, so heating it's a good idea. Notice there will be questions where it's exothermic like a wood fire, and the equilibrium would shift in the wrong direction if this is exothermic. Pressurize it. Right, stick it in a smaller container, squeeze it down, pressurize it. The general rule is pressurizing favors the fewer numbers of moles. In this case, A plus 3B goes to C. That means 4 moles of reactant form 1 mole of product. Yeah, this is a good situation for pressurizing. Fewer moles, 4 compared to 1. So those are the general rules for Le Chatelier's principle. Let's go ahead and apply them, and we'll be done with this whole concept. Imagine we're synthesizing nitrogen dioxide. It's a endothermic process. Here's the chemical reaction. 2 of these plus 1 of those makes 2 of these. Before we even talk about the effects of changes and how they will shift the equilibrium, let's summarize every possible scenario. If we add this, it'll help. If we add that, it'll help. If we take away that, it will help. If we heat it, that will help. If we pressurize it, 3-2, that will help. Those will be every possible case where it'll shift the equilibrium to the right. The only other kind of problem they can ask is taking stuff away. And I usually do an opposite analysis there. If we take away some nitrogen monoxide, that'll be bad. It'll shift the equilibrium to the left because it's the opposite of adding. Get it? Let's go ahead and do every possible scenario. Add reactant. Good. Add product. Bad. Add reactant. Good. And remove reactant. No. Bad. remove product gotta be good, right? It creates a hole, if you will. So if adding product is bad, removing product is good. Remove some oxygen. Why would you want to do that? You need the oxygen. Increase the pressure. 3 to 2, you bet. Increase the temperature. Needs it, so you bet. And you're done. And so that's how we can apply Le Chatelier's principle. These are usually touchy-feely problems like that, and that's how you analyze them. Now, no textbook includes this. That always drives me crazy. But if you are going to do a chemical reaction and you're concerned about equilibrium, you just want a high yield for your reaction. You don't want to shift it. You want to destroy it. And there is an easy way to do that. Remember, it only applies for things that are in solution. So all you got to do is remove, oh, by the way, decreasing, opposite situation. All you got to do to drive a reaction to completion is to remove the product as it's formed. And usually that's easy. If you got to precipitate, it does it for you, right? If you're reacting, doing a chemical reaction, you get wonderful crystals forming as it's doing. That will continuously be removing product, which is right there, removing NO2. You'll be constantly shifting the equilibrium until it's zero because all product has been removed. So there's fancy ways that scientists have come up to do that, figured out how to do that, or there's simple ways. Make one of the products a gas in solution and it's just going to bubble out. Use a solvent in which that gas is totally insoluble. And there's fancier ways as well. But this is the most important thing to know about equilibrium, is it can be eliminated. Okay, that's Le Chatelier's principle.